Compare these two figures, $1,000 sitting on the table today and $1,464.10 available 4 years from now. Finance operates on the axiom that these two sums represent the same amount of wealth. Because money possesses a time value, a single dollar currently in hand is mathematically distinct from a dollar collected tomorrow. We equate them using an interest rate, denoted algebraically as I. This interest rate functions as a temporal exchange rate, the specific metric linking present capital to its future equivalent. Without establishing this explicit rate of exchange, comparing cash flows occurring at different points in time is mathematically invalid. Present dollars must be converted before they can be added to future dollars. Navigating comparisons requires hardware like the BA2+. The third row holds 5 core inputs: N for periods, I over Y for interest, PV for present value, PMT for payment, and FV for future value. Each key triggers a specific algebraic formula. Constructing this mathematical framework from the ground up proves exactly how future benefits are translated into current valuations. Mastering these underlying algebraic mechanics allows an analyst to accurately evaluate and justify large-scale capital outlays. Translating shifting future variables into a single static present-day truth is the foundation of corporate capital allocation. The buildup begins with the basic scenario, pushing an isolated lump sum forward in time. This line graph illustrates the mechanism of compounding. An initial $1,000 present value grows toward a $1,464 future value over 4 periods. Exponential growth is driven by the factor of 1 plus the interest rate, raised to the power of n periods. In the first period, we calculate a 10% interest yield on the original $1,000, arriving at a year 1 total of $1,100. As we progress through years 2, 3, and 4, each calculation compounds upon the previously earned interest. The $1,100 becomes $1,210, then $1,331, finally terminating at $1,464.10. The generalized algebraic equation derived from this progression is FV equals PV times 1 plus I to the power of n. This formula establishes the relationship between 4 variables: future value, the present value starting point, the interest rate, and the number of periods the capital grows. Executing this on professional hardware involves inputting 4 for n, 10 for the interest rate, and negative 1,000 for the present value. The calculator requires the present value to be entered as a negative number to represent a cash outflow, or the initial investment leaving the account. Computing the future value generates the result of $1,464.10, confirming the algebraic derivation. Compounding models the future ceiling of a current investment by leveraging the mechanics of exponential growth over a set timeline. Analysts must also evaluate future promises in present-day terms. Discounting is the mathematical inverse of compounding. By algebraically isolating the present value variable, the formula becomes PV equals future value divided by 1 plus I to the power of n. Moving the exponential curve backward from right to left shows the $1,464 future value discounting down to the $1,000 baseline. Mathematically, present value is the current equivalent of funds slated for receipt at a specific future date. In this reverse operation, the interest rate I serves as the investor's required rate of return, or the discount rate. The hardware performs this inverse operation by taking the future value, the number of periods, and the discount rate to solve directly for the present value. Determining present value is the primary tool used to decide whether future benefits justify current capital outlays. Discounting strips away the illusion of future wealth, providing the exact maximum threshold an analyst should pay today. Isolated single-sum cash flows are rare in corporate finance. Most capital allocation involves series cash flows, where investments involve streams of payments across multiple periods. An ordinary annuity is a series of consecutive, equal payments assumed to occur at the end of each period. We can value an annuity manually by treating every payment as an isolated calculation. This payment at the end of period 3 compounds for 1 period at 10%, equaling $1,100. The period 2 payment compounds for 2 full periods, equaling $1,210. The period 1 payment compounds for 3 periods to equal $1,331. Stacking these individual compounded values, along with the final period 4 payment, reveals the total future value of the annuity, $4,641. While manual aggregation works for 4 years, it becomes inefficient for long-term investments, such as a 30-period corporate bond. The unified future value of an annuity formula, or FVA, collapses these individual calculations into a single operation. The present value of an annuity, or PVA, uses a similar generalized equation to discount a recurring series back to one present-day figure. Recurring series are mapped to the PMT key on the calculator. Here, the A for annuity in our formula translates to the PMT for payment input. Activating the PMT key alongside N, IYY, and PV or FV triggers the complex integrated formulas derived from these first principles. Annuity formulas systematically compress multi-year cash flows into a single metric, enabling rapid capital allocation at scale. This completes the mathematical map required for moving capital through time. We visualize these models using a dual-axis matrix, plotting present versus future value horizontally, and single sums versus annuities vertically. Each quadrant contains its respective formula: single sum future value, single sum present value, future value of an annuity, and present value of an annuity. This underlying logic governs all time value calculations across the financial industry. These formulas dictate the output values found in standard lookup tables used by analysts. Mastering these 4 quadrants is the essential requirement for quantitative financial analysis. At the execution phase of the workflow, the focus centers on the CPT, or Compute, button. Pressing the Compute key executes the precise first principles algebra mapped in this framework. Differentiating between data entry and actual financial analysis requires an understanding of the math behind the machine. The time value of money framework is the bedrock of corporate finance, the tool that allows analysts to translate future realities into precise present-day decisions.